present-day, museum collection, in the quiet, climate-controlled space of a fossil vault. Gloved hands carefully lift a single tooth from a padded drawer. The object is heavy. It feels like dense stone. It does not look like a knife. Instead, it is thick and blunt. It is shaped somewhat like a banana. This is the tooth of an adult Tyrannosaurus rex. Its shape is a highly specific structural design. The enamel is perfectly preserved. But the serrations along the edge are robust, built to withstand immense physical stress. The root alone is massive. It anchored deep into a fused jawbone. This is the hardware of a specialized apex predator, but the story of this animal is completely misunderstood. When we think of this creature, we picture an inevitable king. We assume it was the default giant of the prehistoric world. We assume it was the beginning of a dominant biological dynasty. The physical evidence tells a much different story. The ultimate bone-crushing machine did not appear at the dawn of the dinosaur age. It appeared at the very end. Its reign was brief. Its origins were completely humble. Middle Jurassic, about 166 million years ago. If we step into a reconstruction of this ancient world, the shadows belong to massive giants. The climate is warm and humid. The forests are thick with ancient vegetation. But there is no trace of a gigantic tyrannosaur anywhere in the landscape. The top tier is occupied. Other families of large predatory dinosaurs hold the dominant positions. They stalk the open floodplains. They maintain absolute control over the largest prey species. They will maintain their grip for tens of millions of years. To find the true origin of the tyrant lineage, we have to look away from the final giants. We must examine fragments of bone. These fragments were misunderstood for decades. Present-day context. In the early 20th century, an incomplete fossilized skull was uncovered in European rock layers. The skull was relatively small. It was surprisingly fragile. It possessed a delicate, distinctive crest rising gracefully from its snout. Because of this crest, early scientists originally grouped the animal into an entirely different family of predators. They named it Proceratosaurus. For nearly a century, it sat on a mislabeled branch of the evolutionary tree. It was considered a footnote in the fossil record. Present-day, museum collection. The process of correcting that error requires returning to the physical specimen. It requires measuring what is actually there. Today, researchers do not rely on a single visual feature like a crest to classify an extinct animal. They build massive morphological data matrices. A researcher sits at a computer screen, carefully recording hundreds of minute anatomical details from the skull, the jaw, and the teeth. They measure a single cranial suture. They record the subtle angle of a cheekbone. They assign binary numbers to these features, creating a vast grid of physical traits. They feed this data into cladistic software. The computer maps out evolutionary relationships based on shared physical characteristics. It traces the lineage backward through deep time. That pattern suggests a completely different origin story. Modern anatomical studies reveal that the crest and the subtle shape of the skull belong to a completely different family. Proceratosaurus was not an evolutionary dead end. It was one of the earliest known members of the Tyrannosaur lineage. SRC01. This reclassification fundamentally changes our understanding of the timeline. It pushes the origin back immensely. The family that would eventually produce the final giant had already emerged. They existed more than 100 million years before Tyrannosaurus rex itself existed. That is an almost incomprehensible span of deep time. It is a span longer than the time separating the last dinosaur from humanity. The true history of the tyrant lineage is not a story of immediate dominance. It was a 100 million year waiting game. Middle Jurassic, about 166 million years ago. We can safely reconstruct the earliest members of this lineage as small, marginalized hunters. They lived quietly in the dense forests. They survived by constantly avoiding the larger superpredators of their age. We cannot tell the exact skin color or the vocalizations of Proceratosaurus from this fragmented evidence. What it does support is the animal's position at the very base of the tyrant family tree. SRC01, they were the underdogs of the Mesozoic era. They were secondary predators. For millions of generations, they remain firmly in the second tier of the food chain. They chased small prey while staying entirely out of the way of the ruling giants. But nature was slowly running an experiment in the margins. Long before they gained massive physical size, these small hunters were quietly upgrading their sensory systems. Late Jurassic, about 160 million years ago, the landscape is still dominated by unrelated giants. But the tyrant lineage is quietly diversifying. In the fossil record of ancient Asia, an animal forces us to reconsider their early trajectory. The specimen is named Guanlong. It measures roughly 3 meters in length. It is incredibly slight compared to its massive descendants. It carries a large, elaborate crest sweeping over its snout. SRC02, present-day context. When scientists examine the internal structure of this crest, they find it is highly pneumatic. It is completely hollow. The bone is paper-thin. This tells us exactly what the crest was not used for. The structure is far too delicate for combat. It could not absorb the physical impact of a fight. A conservative interpretation is that it served a visual purpose. Reconstruction, constrained by the fragile bone and modern analogues, suggests the crest was a display structure. It likely functioned for species recognition or attracting a mate. Much like the casques on some modern birds, early tyrannosauroids were highly ornamented animals. SRC02, early Cretaceous, about 125 million years ago. The strange adaptations of the early lineage go beyond fragile crests. In the Liaoning province of China, the fossil of a small predator called Guanlong preserves extraordinary detail. Pressed into the fine-grained sedimentary rock surrounding the skeleton are distinct impressions of filamentous structures. These are primitive proto-feathers. This direct evidence fundamentally alters our view of the early tyrants. They were not scaly. We cannot tell how dense or vividly colored the feathers of Guanlong were from the flattened rock. What the evidence does support is the early presence of integument. Reconstruction, constrained by small body size and heat loss, indicates these proto-feathers functioned as insulation. The small predators needed to retain body heat, but the most critical evolutionary upgrades were completely invisible from the outside. The true advantage was locked inside. Present-day, CT workstation, a digital screen illuminates a darkened laboratory. A researcher scrolls through high-contrast digital slices of a fossilized skull. The physical fossil remains safely on a foam pad. It is entirely untouched by physical tools. The CT scanner has peered through solid rock to map the empty space inside. This empty cavity is an endocast. It is a negative impression of the ancient brain. As the researcher isolates the digital shape, a striking anatomical feature emerges. The olfactory bulbs are massive. Even in these early, small-bodied ancestors, they take up a disproportionate amount of the total brain volume. Early Cretaceous, about 125 million years ago, these scans show that early tyrannosauroids were already highly specialized trackers. They possessed a profoundly sensitive sense of smell millions of years before they grew large. They could detect prey or carcasses over long distances in the dense underbrush. Their sensory software was upgrading. The structure of the skull itself was also slowly changing. Over millions of years, the eye sockets began to shift. They gradually moved forward on the skull. This shift is subtle but crucial. Forward-facing eyes create an overlapping field of view. This generates stereoscopic vision. Stereoscopic vision allows an animal to perceive depth with extreme precision. It turns a flat image into a three-dimensional map. For a small predator navigating a forest, precise depth perception is a matter of survival. A single miscalculation could prove fatal. These are the quiet innovations of the underdog. The lineage is accumulating acute smell, precise binocular vision, and insulating integument. They possess the complex sensory software of an apex predator. But they still lack the massive physical hardware. For 40 million years, they wait. They remain trapped in the ecological margins. They cannot grow larger because the apex niche is fiercely occupied. To become the kings of the prehistoric world, the tyrannosaurs do not need to fight the reigning superpredators. They just need them to disappear. Present-day context. For tens of millions of years, the northern continents are ruled by an entirely different class of killers. The undisputed apex predators of the mid-Cretaceous are the carcharodontosaurids. These are massive, blade-toothed giants. They are specialized for hunting enormous, long-necked sauropods. They hold absolute dominance over the large prey ecosystem. They act as a biological wall. This wall prevents the small, feathered tyrannosaurs from moving up the food chain. SRC-06, present-day, field site. To understand how that wall collapsed, we must leave the museum. We must look at the physical record of the planet itself. A researcher kneels beside an exposed rock outcrop in the American West. The landscape is dry and sun-baked. But the researcher is not looking for bones. They hold a metal trowel. They carefully scrape away loose dirt to reveal a stark transition in the layers of sedimentary rock. The lower layer is terrestrial mudstone. It formed in a coastal environment. Directly above it, the rock abruptly changes to a dark marine shale. This shale is packed with the tiny shells of ancient ocean-dwelling microorganisms. This sharp stratigraphic line is direct evidence of a catastrophic environmental shift. The sea came rushing inland, late Cretaceous, about 95 million years ago. The evidence points to a period of intense global warming. The climate changed drastically. The polar ice completely melted. Sea levels rose higher than they had been in millions of years. This rising water flooded the low-lying plains of the continents. In North America, the ocean cut a massive channel straight through the heart of the landmass. This formed the Western Interior Seaway. The continent was cleaved in two. It created two isolated land masses. These were Laramidia in the west and Appalachia in the east. This geological violence transformed the habitats. It completely altered the vegetation and the food sources of the entire ecosystem. Present-day context. The massive carcharodontosaurids were highly specialized. They hunted giant sauropods in vast, stable environments. When the climate shifted and the environments fragmented, their specific food web collapsed. The fossil record clearly shows that by roughly 90 million years ago, these giant predatory groups disappeared entirely from the northern continents. While the exact cause of this turnover remains debated, the fossil evidence of their absence is clear. SRC-06, late Cretaceous, about 90 million years ago. The disappearance of the ruling giants left a massive vacuum. The ecological niche for a large apex predator was suddenly vacant. The tyrannosaurs did not defeat the carcharodontosaurs in combat to claim the throne. They survived an environmental catastrophe. That catastrophe wiped their rivals out. We cannot tell exactly how the last carcharodontosaur died from the stratigraphy. What the evidence does support is an ecological replacement driven by climate opportunism. Once the barrier was removed, the tyrannosaurs began to scale up. The wait was over. Intermediate species in the fossil record reveal this rapid transition. Animals that were once the size of a wolf evolved into larger forms. They became predators the size of a horse, and then the size of a modern rhinoceros. They kept their highly advanced sensory software. They retained their acute smell and stereoscopic vision. But now, they rapidly expanded their physical hardware. They stepped into the empty throne. The stage was finally set. It was the ultimate biological experiment in gigantism. Once they claimed the top tier of the food web, natural selection pushed their growth rates to an astonishing extreme. Late Cretaceous, about 68 million years ago. The environment of Laramidia is dense and heavily forested. The ecosystem is completely transformed from the Jurassic. The ruling giants are gone. In their place stands the final, hyper-specialized product of the tyrant lineage. This is Tyrannosaurus rex. It is massive. It reaches lengths of about 12 meters. Roughly the length of a city bus. It is an apex predator of unprecedented scale. But the true secret of its dominance is not just its final size. It is the extreme biological mechanism it used to get there. Present-day, histology lab. To understand how a small underdog evolved into a 9.000 kilogram giant, we must look inside the bone itself. A technician operates a diamond-tipped rock saw. Sparks and a steady spray of cooling water fly from the blade. It cuts a thin cross-section from a fossilized T-Rex fibula. The technician grinds the slice down until it is paper-thin. They mount it onto a glass slide, present-day, microscope workstation. The slide is placed under a polarized light microscope. On the digital monitor, the dense rock resolves into a detailed landscape of cellular structure. The image shows a series of dark, concentric rings. They circle the center of the bone. These are lines of arrested growth, or lags. SRC03, much like the rings of a tree. These lines form annually. During seasons when food is scarce, the animal's growth slows down. This leaves a dense line in the bone tissue. By counting these lines, scientists determine the age of the animal at death. The data extracted from these microscopic slices is shocking. The rings tell us that Tyrannosaurus rex did not live for a century. The maximum lifespan of the species was roughly 28 to 30 years. It was a fast, violent life cycle. Present-day context. Researchers measure the circumference of the bone at each annual growth ring. This allows them to calculate the mass of the animal at that specific age. They map these data points across multiple specimens. A clear mathematical curve emerges. The growth curve is explosive. Between the ages of roughly 14 and 18, the animal entered a period of extreme adolescent development. During this teenage growth spurt, it gained an average of about 600 to 760 kilograms per year. That is equivalent to adding the weight of a small car to its body every single year. SRC03, late Cretaceous, about 68 million years ago. This extreme growth rate created a strange dynamic in the prehistoric forest. We cannot tell the social behavior of a teenager from these bone slices. What they do support is an explosive metabolic shift. This shift functionally separated the generations. A juvenile T-Rex had dramatically different limb proportions than an adult. It had long, slender legs and a lightweight body. It was built for speed and agility. Reconstruction, constrained by these physical proportions, suggests that juveniles chased small, fast-moving prey. They functioned as entirely different predators. SRC03, by the time the animal reached adulthood, its body had transformed. It became a heavy, bone-crushing machine. It was now built to tackle massive megaherbivores like Triceratops and Edmontosaurus. This ontogenetic niche partitioning is the true secret of their dominance. A single species occupied multiple predatory niches at the same time. The juveniles controlled the mid-tier of the food web. The adults controlled the very top. The adult T-Rex survived the most dangerous growth spurt in the history of land predators. To fuel that massive adult body, it needed to kill massive prey. It needed a biological weapon capable of instantly shutting down a fight. Present-day, prep lab. A technician leans over a sturdy wooden workbench. They wear a respirator mask and protective glasses. In their gloved hands, they hold a pneumatic air scribe. It buzzes loudly. A fine metal tip vibrates against dense rock matrix. The tool carefully frees the root of an adult Tyrannosaurus rex tooth. As the matrix clears, the true scale of the weapon emerges. The tooth is not a thin blade. It is not meant to slice flesh. It is thick and blunt. It is nearly circular in cross-section. It is a structural spike. The root is massive, designed to anchor deep into the jawline. This tooth serves one specific mechanical purpose. It is built to shatter solid bone. Present-day, digital biomechanics. Understanding this weapon requires testing the structural limits of the skull itself. A researcher sits at a computer. They load a high-resolution 3D digital mesh of a T-Rex skull into specialized software. This is finite element analysis, or FAIR. This software was originally designed to test the stress limits of bridges. The researcher applies digital force to the jaw muscles of the virtual skull. This simulates the mechanics of a bite. SRC04, on the screen. The wireframe skull glows with a thermal heat map. Blue indicates areas of low stress. Red and white indicate extreme structural tension. As the simulated jaws clamp down, the colors shift violently. The forces are immense. But the skull does not break. The digital model reveals that the nasal bones are fused tightly together. They act exactly like the load-bearing arch of a stone bridge. They distribute the catastrophic force safely across the heavy skull. Present-day context. The engineering models suggest the entire architecture of the head is optimized. It is designed to deliver crushing power. One biomechanical model estimates that an adult T-Rex could generate a maximum bite force between 35.000 and 57.000 newtons. That is roughly equivalent to the weight of a pickup truck concentrated onto the tip of a single tooth. SRC04. We cannot tell the exact muscle fiber density from fossilized attachment points. What the models do support is the overall skeletal load-bearing capacity of the skull. It was a machine built for extreme trauma. Present-day, museum collection. The physical proof of this power comes from fossilized remains. In a specimen drawer, a researcher examines a lumpy mass of fossilized feces. This is known as a coprolite. This particular coprolite is attributed to T-Rex. When the interior is analyzed, it is not just composed of digested soft tissue. It is packed with thousands of jagged, pulverized bone shards. This is direct evidence of osteophagy. T-Rex crushed the skeleton. It consumed the bone to extract rich marrow and essential minerals. The adult T-Rex possessed the hardware to shatter prey. It had the software to track it over long distances. It had the biological necessity to consume entire skeletons. It was a devastating biological machine. But the sheer power of this machine sparked a bitter debate. A massive bite force is incredibly useful for crushing a dead carcass. But did this heavy animal actually have the speed to hunt a living one? Present-day context. For decades, the popular image of Tyrannosaurus rex was an unstoppable, sprinting killer. But as paleontology transitioned into a precise, data-driven science, that image faced intense scrutiny. In the early 1990s, an alternative hypothesis emerged. An earlier hypothesis argued that T-Rex was not an active hunter at all, but rather an obligate scavenger. The argument was based on physical constraints. The animal had disproportionately tiny forelimbs. It had massive olfactory bulbs, perfect for smelling rotting meat. Most importantly, its sheer bulk made high-speed pursuits biomechanically questionable. Present-day, digital biomechanics. The question of speed is a matter of physics. Biomechanical engineers return to the digital models. They focus on the stress limits of the leg bones. An adult T-Rex weighed roughly 9.000 kilograms. When an animal runs, the force of impact on its feet multiplies exponentially with speed. The digital simulation tests the limits of the fossilized femur. The results are decisive. If a 9.000 kilogram animal were to sprint, the impact force would shatter its own leg bones. Current models constrain top speeds to the order of 16 to 29 kilometers per hour. That is not a sprint. That is a fast walk, or a slow jog. If T-Rex could not run down healthy, fast-moving prey, the scavenger hypothesis gained traction. To resolve the debate, science needed something beyond computer models. It needed physical, forensic proof of a hunt. It needed a survivor. Present-day, prep lab, X-ray, In a paleontology lab, a researcher examines a large, jacketed fossil. It is the tail vertebra of an Edmontosaurus. This massive herbivore shared the Hell Creek ecosystem with T-Rex. The bone is strangely deformed. A large, bulbous mass of irregular bone growth surrounds a deep puncture wound. The fossil is placed into an X-ray machine. The high-contrast image reveals a stunning secret inside the matrix. Embedded deep within the vertebra is the unmistakable crown of a Tyrannosaurus rex tooth. SRC05, present-day, context. This single piece of physical evidence unravels the obligate scavenger hypothesis. The irregular bone growth is an infection response. The bone had healed over the tooth. This means the Edmontosaurus was alive when it was bitten. The prey was living. It was attacked. It survived long enough for its skeletal tissue to completely heal around the predator's broken tooth. We cannot tell how many hunts ended in failure from this single pathology. What this healed bone supports is that they actively engaged and attacked living targets. SRC05, Late Cretaceous, about 68 million years ago, reconstruction. Constrained by modern apex predators and this forensic pathology, paints a clear picture. Tyrannosaurus rex was an opportunistic predator. Like modern lions or bears, it would readily scavenge a free meal to save energy. But when required, it was a terrifyingly capable ambush hunter. It used its acute sense of smell and stereoscopic vision to locate vulnerable prey. It did not need to sprint at high speeds. It only needed to close the distance enough to deliver one catastrophic bite. The presence of this massive opportunist created a permanent landscape of fear. Herbivores altered their migration routes. Smaller predators waited in the margins. The entire ecosystem bent around the biological gravity of the tyrant king. It was an empire built on hyper-specialized perfection. But biological perfection is a dangerous trap. Late Cretaceous, about 66 million years ago, the tyrant empire is at the peak of its reign. Across the humid, forested floodplains of Laramidia, Tyrannosaurus rex holds unchallenged dominance. The 100-million-year waiting game has culminated in a biomechanical marvel. The adults govern the mega-herbivores with a 57.000 Newton bite force, while the fast-growing juveniles dominate the mid-tier of the food web. The sensory software is flawless. The structural hardware is devastating. The lineage has adapted perfectly to this specific, stable environment, but evolution has no foresight. The more perfectly an organism adapts to a specific world, the more dependent it becomes on that world remaining exactly the same. Present-day, field site, in a dry canyon. A geologist carefully brushes away the last layers of dirt on a vertical rock face. The stratigraphic column is clearly visible, reading like a timeline stacked in stone. The lower layers are rich with the bones of Triceratops, Edmontosaurus, and T-Rex. But the trowel points to a strange, dark band of rock no thicker than a human finger. This is a layer of iridium-rich clay. Iridium is extremely rare on Earth's surface, but it is abundant in meteorites. This thin line of sediment is the physical footprint of a global catastrophe. It marks the exact boundary where the Cretaceous period ends. Late Cretaceous, about 66 million years ago, an asteroid roughly 10 kilometers wide strikes the shallow waters of what is now the Yucatan Peninsula. The impact releases energy equivalent to billions of atomic bombs. If a T-Rex is standing in the forests of Hell Creek, thousands of miles away, the initial blast wave is not the immediate killer. The true catastrophe unfolds in the dark. The impact violently ejects billions of tons of vaporized rock and sulfur into the upper atmosphere. The debris forms a dense, global veil. It blocks the sun. Earth enters a sudden, brutal impact winter. Present-day, context, without sunlight. Photosynthesis halts. The massive ancient forests wither. As the plants die, the giant herbivores, the Triceratops and the Edmontosaurus, starve. And as the herbivores die, the apex predator is trapped by its own extreme success. A 9.000 kilogram predator with an explosive metabolic rate requires a staggering daily intake of calories to survive. A T-Rex cannot sustain itself on insects, small mammals, or sparse vegetation. Its body is highly specialized for one task, bringing down massive prey. When that prey vanishes, the massive bite force, the binocular vision, and the crushing teeth become entirely useless. We cannot tell exactly which day the last T-Rex died from the stratigraphic record. Some individuals likely survive for months, aggressively scavenging the rotting carcasses of the collapsed ecosystem. What the stratigraphy supports is a rapid, catastrophic collapse of their food web. The perfection of the predator was its very undoing. Present-day, museum collection. Back in the quiet vault, the massive, banana-shaped tooth rests safely in its foam drawer. It is a monument to an incredible evolutionary journey. The tyrant lineage spent 100 million years in the shadows, quietly upgrading their senses and surviving in the margins. When the climate cleared a path, they seized the empty throne and exploded into the most terrifying bone-crushing machines ever to walk the earth. But their reign at the absolute top was geologically brief. When the world changed overnight, the giant kings starved. The only dinosaurs that survived the ash and the cold were the small, generalized, feathered underdogs, the ancestors of modern birds. The legacy of Tyrannosaurus rex is not a story of inevitable dominance. It is a harsh reminder of a universal biological truth. No matter how massive the hardware, no matter how perfect the adaptations, no absolute power can escape the changing of the earth. The greatest predator in history was simply a brilliant, temporary opportunist, waiting in the dark for a chance that eventually destroyed it.